Hello, my name is Mark Baggett, and I'm going to be talking to you today about working with different bases. In information security, in IT in general, we often have to deal with numbers that are presented to us in base 2, base 10, and base 16, so it's important to understand those. Let's discuss those here. So, by way of introduction, let me tell you a little bit about myself. My name is Mark Baggett. I'm a penetration tester and incident response consultant. I'm also a senior instructor for SANS and the author of a couple of different courses, including SEC 573, which is my automating information security with Python class. Here, I'll assume you know no coding. We'll come in, we'll learn how to develop simple programs that you can use in defending your network, doing penetration tests, or building forensics tools. So how to build a simple interpreter-like functionality into a backdoor, how to analyze logs and be able to identify attackers in those logs in an automated way. Forensics, how to build tools that can parse through binary structures, extract artifacts from them. That's 573 and 673. We pick up right where 573 left off, which is my advanced coding class. This one I'm going to assume you know how to code coming in to 673. We're going to talk about object-oriented coding. We're going to talk about unit tests. We're going to talk about how to do parallel processing with multi-processing, multi-thread, how you could spread that out across cloud-based instances. We'll talk about logging, the proper way to log our systems. We'll talk about various attacks that can occur in Python, like serialization attacks and web frameworks, how we can attack those, and how to defend against those as well. SEC 406 is my introduction to Linux class. So if you're brand new to Linux and you want to know how to secure your Linux environment, how to operate in a Linux environment to run all of those awesome information security programs, then SEC 406 is a great class for that. I do have a master's in information security, and I was the 15th person in the world to get to the GSE. Today, I serve in a role where I'm an advisor to the DoD. I am a former chief information security officer and a veteran. I got lots of experience. This last little thing is kind of neat. If you grep for my name recursively, ignoring case, in the Metasploit framework, and then pipe that to word count, you'll see that my name appears in Metasploit 7 times. Now, this is not because I wrote anything for Metasploit. This is people who have written things for Metasploit have given me credit because of different tools and techniques that I used that implemented these different attack scenarios in other platforms have been developed in the Metasploit framework. So that's kind of neat. Let's talk for a minute about how we represent natural numbers. Natural numbers are called natural numbers because they just kind of appear in nature, right? We all have a universal understanding of what these numbers are. It's not like they're a subjective understanding that each individual imagines what numbers are. These numbers have something to do with reality, the reality around us. It's fascinating to me that mathematical functions could prove the existence of the Higgs boson particle decades before we could ever empirically test and see that, well, it really is a thing, right? Numbers represent actual properties of reality. If I have one chicken in the room and then I bring another one chicken into the room, then I now have two chickens in the room. There's actual values about these objects have properties, and those properties are based in reality. Now, there's different ways we can represent these numbers, different symbols we use to use the number one. For example, when we're talking about Roman numerals, the different Roman numerals that you'd see associated with the Super Bowl, right? They'd use different letters to represent those numbers. Now, we have different counting systems is another way of saying that. So I have base 10 is how we would typically count with the numbers 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. That's most commonly used numbering system we're used to, but certainly Roman numerals would be another example of a completely different way that we can represent numbers and present those. Two others that are very important to us in information security are base 2, binary, base 16, which is hexadecimal. Also, there's octal, which is base 8, use those in Linux permissions. We're not going to talk a whole lot about base 8, but if you understand how base 2, base 10, base 16 work, then understanding what octal is doing is really no different. So let's talk about how we count here, and I'm going to use some Python to show you that. I'm going to import time so I can get a little bit of a delay. I'm going to say for I in range 10,000. What I want to do is I just want to print. I'm going to use an F string, and I'm just going to print I, but I want it to have leading zeros and make it 10 digits wide. All right. And then I also don't want to press enter at the end of each line. I want it to move back to the beginning of the line. So I'll do that. And then I'll just sleep for time.sleep for, we'll just do 1/10 of 1 second. Okay, so what we have here is a little counter that's running in our program. This is counting the same way that we do. And what I want you to notice here is in the least significant digit, the least significant bit here, or not, we'll call it the least significant place, also known as the tens place. It's just counting 1 through 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9 over and over again. And then every time we reach 9, when we've run out of numbers in that spot, we increment the tens place. The tens place goes up by 1. And likewise, the tens place is going to, once it gets to 9, it goes back to 0, and then we increment the 100s place. When the hundreds place eventually reaches 9, which I don't think we'll get to see here, once that reaches 9, then that increments the 1000s place, and so forth. So because we have 9 digits, right, 9 fingers and toes on us, we count in base 10. But it's really, we're just cycling through the numbers here. Every time we reach a number, we increment the next spot, and then we reset the previous number, and we keep going on. Now this is true for the counting in tens, but it's also true for counting in hexadecimal and others as well. So here, I've got some code that I don't want you to have to watch me type this over and over again. So this is counting in hexadecimal. So over here you see the hexadecimal numbers, and you'll notice that it counts through 0 through 9. And then because hexadecimal is base 16, once we've reached 9, then we have to go on with other letters. So we use A, B, C, D, E, and F to represent the numbers 10, 11, 12, 13, 14, and 15. So once we get to F in this case, then that resets back to 0. And then we increment the 16s place, and then it increments. So here you can see 6, 7, 8. We're about to get to 9, and then we'll go into our first A. And then once we've done that, B, C, D, E, and F. Once we reach F here, then this next spot, which is going to be 16 cubed increments, so from 1 to 2. So this is actually, we can store the values 1 through 16 here. And then once we have a version of 16, we say, okay, now we have 1 16, then we have 2 16s, and we have 3 16s. So this is actually, this position here represents 16 squared, and this number represents 16 cubed, and 16 to the 4th, and 16 to the 5th, and 16 to the 7th, and so forth. This is true also for base 2, when we want to count in binary. Let me just grab some code that's going to print that out in binary, and just so you don't have to watch me type this out, I've pasted this in for you. And so here we're counting in binary, where we only have 2 values. With binary, you only have the values 0 and 1. But it works the same way. Notice that this first digit is cycling 0, 1, 0, 1, 0, 1. And every time it reaches 1, which is the maximum number of digits we have, then this bit here increments. Now, with 0 and 1, I can store the numbers 0 and 1. So every time I reach run, then I say, okay, now I've had 1, 0, and 1, which means that this is actually the 2's place, and then this would be the 4's place, 8, 16, 32, 64, 128, and so forth. But you'll notice that this just keeps going back and forth, and every time a value in a position reaches the number 1, then we increment, when we increment the digit next to it, and this is how we can count in base 2. So that's base 2, base 16 counting. I want you to recognize that it really is just rolling over those bits to the next number. and pushing those values out further to the left. Okay, but we are accumulating those values. It works the same in binary as it does in base 10. It works the same in hexadecimal as it does in base 10. Let's review some concepts of exponential math for just a second. Right? So an exponent describes the number of times that you multiply a number by itself. So this is 10 multiplied by itself 2 times would be 10 squared. So that's 10 times 10, which is equal to 100. Or 10 to the 6th is 10 multiplied by itself 6 times, or 10 times 10 times 10 times 10 times 10 times 10, or a million. Now, this is true. In this case, we're doing base 10, but whether we're doing 2 to the second power, 2 to the second power would be 2 times 2. 2 multiplied by itself 2 times. Right now, one attribute of exponent math that is a little confusing or not so intuitive is 10 to the 0th. Anything to the 0th power is equal to 1, not 0, but 10 to the 0th power is 1, and any number to the first power is equal to itself. So when we're talking about decimal numbers, what we're really doing is we're taking, this is the tens place, this is the 100s place, this is the ones place, the tens place, the 100s place, and the 1000s place. So what we're really saying is this is 10 to the 0th power. This is 10 to the first power, which is 10, 10 to the second power, and 10 to the third power. So we're going to increase the exponent for each of these places as we move up. And if I had a fifth digit here, it would be 10 to the fourth, 10 to the fifth, and so on as we move up through the digits. So when we're calculating a base 10 number, what this is really saying, all right, this is 5 times 10 to the third, or 5 times 1,000, which is equal to 5,000. This is 7 times 10 squared, which is 7 times 100, which is 700. And this is 3 times 10 to the first. Anything to the first power is itself, so this is 10 times 3, which is 30. Plus, this is 10 to the 0th power. Anything to the 0th power is 1, or so 0 times 1. Well, in this case, it's 0. So this number is 5,730, but we get that by adding up each of those values that are associated with it. Now, if you think of it that way, then what we do with base 2, base 16 really makes perfect sense. Now, when we count in decimal, we count in base 10 because we have 10 fingers and toes, so it's very natural for us to count in base 10. But computers don't have fingers and toes. Well, I would say more accurately, or a better analogy would be to say that computers have one finger, and that finger is either up or it's down. Right? They have two states. Right? They either store a voltage or they don't store a voltage. In memory chips, right, there can be a voltage present in the JK flip-flop, or the microchip that is storing that value, or it can be absent. So we would say if it's present, that'll be a 1. If it's absent, that is a 0. And on a hard drive, we have the presence of a magnetic field on a hard drive, which is used to store the value 1. And the absence of that field in that same spot would store the value 0. On old compact discs or DVDs, right, you would shoot a laser into a spot, and if it reflected that light back, then that was a 1. And if it had a hole burned in it by the writers, then it would not reflect that surface back, or that light back, and so that was a 0. But these two states of 1s and 0s are used with computers, and so if we only have one finger that we can put up or down, we're going to have to use a different numbering system in order to store larger values, and that is binary. So here you see a picture of a building that has 1, 2, 3, 8 different windows, and those windows, they have lights in those, and those lights can be stored. Those lights can be on or off, and so here we could actually represent a byte of data, which is 8 bits, having this one, each of these windows represent a different bit, so that we can have a 0, 0, 0, 0, 1, 0, 0, 1, which is stored in the presence of lights in a building. So we can represent and store numbers just about anywhere if we use binary representation. You'll remember from our earlier looking at how we could count in binary that this number 0 and 1 is the one we're going to flip first, right? That is going to be our 2 to the 0th power. That's going to represent either the number 0 or 1. This number, just like with base 10, this is going to be 2 to the first power. 2 to the first power is 2. 2 squared is 2 times 2. So this can store the number 4. 2 to the third, this is going to store the number 8. So we're going to use these, and we would continue this going on and on if we had more digits that we wanted to store. But here we're just looking at a 4-bit binary number. So what is the number 1101 when stored in binary? Well, we can use the same mathematical principles that we used for base 10 to do that value. We're going to take this number here, the 0 or the 1, times whatever the value that we can store in that position. So when we do this, this would be a 1 times 2 to the third. So that's 1 times 2 to the third is 8, which means we are going to have 8 in our final value. This number here would be 1 times 2 to the fourth. So we're going to have that 4 is going to be stored in our final value. This is 0 times 2 to the first. 0 times anything is 0. So the fact that that means I do not have anything in the 2's place. So it's going to be a plus 0. And then finally, I do have a 1 in the first place, or 2 to the 0th place. That's 1 times 2 to the 0th. 1 times 1 is 1. So we're going to add this. So this is the number 13 stored in binary. But you can see that it's being stored and presented the same way that we do with decimal numbers. We just have different bases and, well, our exponents as we move up. It's still 0, 1, 2, 3, 4, and so forth. We just are changing the base as we do our math. With hexadecimal, we have 16 possible values. So here we're still going to use our numbers 0 through 9 to represent numbers, the first 10 numbers. And then we're going to also have A, B, C, D, E, and F represent the other values that we can store in, if we have 16 possible states, or 16 fingers, right? If we had 16 fingers, we would need to call those other fingers some numbers. So we use A for the number 10, B for 11, C for 12, D for 13, E for 14, and F for 15. So that's 16 possible values, 0 through 15. Okay, so we do need 4 binary bits in order to store 16, right? 16 bits. So with 4, remember that's 1, 2, 4, and 8. If we had 1 in all of those positions, it would add up to 15. We'll take a closer look at that in a little bit. Okay, so how do we decode hexadecimal? What is the number 12AF in hexadecimal if we wanted to convert that into binary, into decimal? Well, this would be just changing the base, 16 to the 0th power, 16 to the first power, 16 squared, 16 cubed, and again 16 to the fourth, and so forth. We needed more digits. So this first one can hold up a value. We'll call this the 1's place, the 16's place, the 256's place, and the 4096's place. Which means that to calculate this, it's going to be 1 times 16 to the third, or 4096, plus 2 times 16 squared, or 2 times 256, which would be 512, plus 10 times 16, which would be 10 times 16. A is the number 10. That's going to be 160. So 160 plus F, which is 15 times 1. It's going to be plus 15 there, which is going to give us that value there. So we can do that type of math in our heads if we were really trying to understand what these components were. But there's This multiplying by 16, right? I used 1 and 2 here because, well, this math can get pretty complex pretty quick, right? If this is an F here, well, what's 15 times 4096? Quick, quick. All right, well, without doing it with a calculator, that's going to take some thinking, right? So we want to look at some ways that we might be able to do conversions between these bases without having to use a calculator. A great shortcut is the fact that all of the powers of 2's have relationships to one another. So with binary, well, a single bit in binary is represented with a single binary digit. But in octal, which is 2 to the third, since it's also a power of 2, right? Octal, 2 to the third power, we now just need to we can look at any 3 bits in a binary number as an octal number and convert directly between them. Similarly, 2 to the fourth, which is hexadecimal, is base 16, any 4 digits can be used to store a number. And because these are all powers of 2, we can easily convert back and forth between them. So let's look at a shortcut for how we can convert base 16 into base 2 quite easily. Now I can only do this because they're both powers of 2. I can't do a shortcut like this to convert between base 16 and base 10, or base 16 and base 15, or any of the other things that are not powers of 2. But because these are both powers of 2, I can use a trick. What I can do is, well, every single one of these octal codes is a value between 0 and 15. 16 possible values, which is 4 bits, right? So the letter B, which is the number 11 in decimal, I can store that in its binary representation. So here I've got a 1 in the 8's place. I have a 0 in the 4's place. I have a 1 in the 2's place and a 1 in the 1's place. So this is 8 plus 2 plus 1, or an 11. So I can just take that B and convert it into binary very simply. Now, that this is a 4-digit number, but the fact is that I can ignore the fact that this is a 4-digit hexadecimal number and simply convert each character into their 4-byte association. So the number 3, I'm just going to put a 1 in the 2 spot and a 1 in the 1 spot to represent the number 3. For the number C, well, the C is the number 12, so that's going to be an 8 plus a 4, and then nothing in the 2's and the 1's. So I just simply convert that. And then 5, well, that's going to be a 4 and a 1. So I'm going to put a 1 in the 4 spot and a 1 in the 1 spot. And so I've converted each of these characters individually, and then if I want to know what that is in binary, I'll just combine those digits, right? Just put that into one big binary number, and that is that number. Now the same would be true in converting binary into hex. So if I had this string of 16 ones and zeros in base 2, and I wanted to convert it into hex, well, I could just break it down into those 4-digit components. So here I've got these sets of ones and zeros. I'm just going to separate these down into 4-digit or 4-bit components, and then I can convert each of those manually. So 1, 0, 1, 1 is an 8 plus a 2 plus a 1, which is 11. So this is a B. So I can put a B there. The second one is a 1, 0, 0, 1, 0. That's a 0 in the 8's place, a 0 in the 4's place, a 1 in the 2's place, and a 0 in the 1's place. So this is the number 2 in binary. And this is a 1, 1, 0, 1. So I've got a 1 in the 8's place. I've got a 1 in the 4's place. I have zeros here, so it's going to be a 4 plus 2, which is 12. This is C. So this in hexadecimal is C2B. So converting back and forth between base 2 and base 16 are very simple. We can simply treat them as 4 bits at a time. Now, if this was octal, right? If it was octal, then, well, I would break it down into 3 bits, because base 8, I need 3 bits in order to store a number between 0 and 8 for the octal bits. But what about hexadecimal to decimal, or bin to decimal. Since base 10 is not a power of 2, you cannot easily convert between these things. There's no simple trick to do this. But I find that, you know what, doing base 2 math, multiplying by 2, is pretty easy. But multiplying by 16, not so easy. So if you wanted me to go from hexadecimal down to decimal, I would, and I didn't have a calculator in front of me that I could just pull up and do these calculations for me. I was forced to do this in my head. Well, I would go through binary on the way. So I would convert hex first to binary and decimal. And this is true anytime I'm dealing with the decimal numbers. Usually converting these things to binary rather than directly to hex is going to be an easier way to go. So let's just compare the two processes that I have to go through with using bin, binary as an intermediary, and without. All right, so let's go from base 16 straight to 10. All right, what do I have to do if I want to convert this base 16 number to 10? Well, the first thing I have to do is I have to take, all right, 16 to the 0th, 16 to the 1, 16 squared. So I have to say, what is C, which is 12, times 16 squared? What is 12 times 256? Can I do that in my head? Well, let's see. I can say 256 times 10, right, is 2,560, and then I'm going to add 256 two more times, so that would be another 512. So 2560 plus 2512. All right, even that, right? I'm already getting a headache, but well, and that is, yeah, okay. Plus, yeah, 2560 plus another 512, 3072. All right, so yeah, there's a bit of complex math that I've got to do in order to get that done. How about this one? 2 times 16. All right, I can do that one. Plus 32. Right, I can do that one in my head. How about B? B is the number, A is 10, B is 11. This is going to be 11 times 1 plus 11, so that's 3115. Okay, so that's doing it straight. I have to do a bit of complex math, and now imagine this is a 4-digit, so I'm multiplying 12 times 4096, or a 5 hexadecimal characters. The math gets more difficult pretty quick. Using binary can help us out with this. So if I do this by going through base 2, well, now the math is easy, right? This B, hexadecimal B, well, I can easily, we've already seen that we can just convert that into the 4 bits, right? B is going to be an 8 plus a 2 plus a 1, that's 11. My 2 is here, and my C is 12. It's an 8 plus a 4. So these 3 are very easily done. So now that I've got it in binary, how do I take binary back to base 2? Well, this is 2 to the 0th, which is 1. This is 2 squared, which is 2. 2 to the 3rd, which is 4. 2 to the 4th, which is 8. And I want you to notice 1, 2, 4, 8. Every single time, the place just gets multiplied by 2. So this is 8 times 2, 16, times 2, 32, times 2, 64, times 2, 128. I can multiply by 2 all day, 4096, right? Keep going up on the numbers. We can just multiply by 2. That's pretty easy math. So now it's just a matter of adding up 1, which 120, 48, right? Plus 1, 10, 24. We got none of those, none of those, none of those, none of those. 132, none of those. 1, 8, one of those. A 2. So this, to me, is easier math than having to multiply by 16. So oftentimes I'll go through our base 2s, and because I can easily convert from hexadecimal to binary, right, then this first part is trivial. And then it's just a matter of multiplying by 2s, which in my mind is easier than multiplying by base 16s. All right, so let's do a little bit of practice of this. I'm going to run this program called Base Practice, which you can find a link to this in the video if you'd like to do some of these. And so this is just a little Python program I wrote that'll let us practice converting between these different numbers. So let's do something really simple first. Let's do hex to binary. Let's do number 6. Right? And so this is going to ask me, what is this 0A in binary? Okay, so now I could say, okay, well, this is the number 10, and then do this. And actually, the fact that this first digit is 0 makes this one pretty easily, trivially easy. But I'm going to point out that what I'm going to do here is I'm going to first convert the 0 into 4 binary bits, 1, 2, 3, 4. Then I'm going to convert the number A, which is a 10, which is going to be an 8 and a 2. So I'm going to say 1 in the 8's place, 0 in the 4's, 1 in the 2's place, and a 0 there. Okay, and I press enter. You can see I got that correct. All right, so I've got 1 of 5. I got to go through 5 of these things. All right, so now what about D7? This one, the math is a little harder if I was going to try and convert this directly, but I don't have to. I can just say, what is the value for D? Well, a D is, let's see, A is 10, B is 11, C is 12, D is 13. So that's going to be an 8. Plus a 4 gives me 12, and then a 1, that's the number D. So I'm just converting this first digit. Now I have to say, what is a 7? Well, there's nothing in the 8's place, and I got a 4, a 2, and a 1. And I can get that one correct. How about 9C? I'm going to put my 0B, then I'm going to put a 9, I'm going to have a 1 in the 8's, and I'm going to have a 1 in the first place, and then the number C is the number 12. So that's going to be a 1 in the 8, 1 in the 4's place, and then 2 zeros on the next one. How about ED? It's going to be a 0B. So I know that F is 1, 1, 1, 1. So when I see the number E, I know, okay, that's 1 less than that. So I kind of do some backwards math whenever I see E or some value that's off from a value that's at the maximum number of flags there. And then D, well, that's actually just 2 off from F, so that was going to be a 1, 1, 0, 1, just like that. Okay, enter that. We'll get that one correct. How about this one? BD, 0B. All right, a B is A is 10, B is 11, so that's going to be an 8 plus a 2 and a 1 is B, and then D is going to be 1, 1, 0, 1. All right, so that's an 8 plus a 4 is 12, and then 1 is 13, which is the number D. All right, enter that one, and I got all of those correct. So that's hex to binary. Well, how about some binary to hex? I could do number 5 here. This one's okay. Same thing. I'm going to break these down into 4 bits at a time. I'm going to say the answer is going to be 0x. This is 1, 1, 1, 0. That's an 8 plus a 4, 12, plus 1 is 13. That's a D. And then this is 8 and a 1, D9. Okay. Incorrect, E9. Let me see. 8 plus 4 is 12, plus 2 is 14. Yes, it is an E9. I did my math wrong. Okay. Easier, but still not perfect. All right, let's go with it. What's this next one? We got a 1, 1, 1, 1. That's an F. Okay, and then, 0, 1, 1, 1, 1. That's not an F. That is a 4 plus a 2 plus a 1. So that's a 7. And then we have a 1, 1, 1, 0. That's an 8 and a 4 is 12. Plus a 4. Not going to get me this time. It's a 7E. Okay. All right, how about this one? That's going to be a 1 and an F. So 0x1F. Let's see here. What's this next one? That's going to be a 2 and an E. So 0x2E. How about this one? This is going to be an 8 and a 4. That's going to be a 12 and a 0. 12 is ABC, so 0xC0. What? I got that wrong. Oh, is A0? Wait a minute. 8. Oh, 8 plus 2. Oh, 8 plus 2. All right, it assessed a penalty to me, so it increased my required challenges by 2. Obviously, I need more practice here. So over here in my score, I can see I've got to get 4 more right, and I now have 2 strikes before another penalty is assessed. So what is this one? It's a 0xf, and an 8 and a 2 is a 10, so it's a 0xfa, and so forth. All right, you get the idea there. Let me try a different one of these. Let's do, so this first one, decimal to binary. So when doing binary, I've got to, well, do some division. I know that my first most significant bit in 8 bits with binary, right? This is 1, 2, 4, 8, 16, 32, 64, 128. So this is more than 128, so I'm going to put a 1 there. Then I'm going to subtract 128 from that to see what is it that I have left. Well, 128 or 133 minus 128, I have 5 left. So I need to represent a 5, which I can do with a 1 and with a 4. So these two are the 4 and the 1 space are going to have 1s. Everything else is going to be a 0. So I will do that like this. I'll say 128, 64, 32, 16, 8, 4, 2, 1, and then I'll count my digits. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7, 8. Looks good. Got that one correct. How about this one? 67. Well, this is 1, 2, 4, 8, 16, 32, 64 plus 3, which is a 2 and a 1. So that's going to be a 0, be no 128s, 164, no 32s, no 16s, no 8s, but I have a full, no 4s, I have a 2 and a 1. Okay, we'll get that one correct. All right, so that's how we can do decimal numbers. Let's get out of there. Let's try a different one. How about a binary to decimal? I'm gonna, notice these have some easy ones and they have some hard ones. The easy ones in here are pretty close to powers of 2. So in this case, you can see that it's putting ones in significant spots. So 1, 2, 4, 8, 16. That's number 16. All right, how about this one? 1, 2, 4, 8, 16. Oh, wait. 1, 2, 4, 8, 16, 32, 64, 128. That's the number 64. How about this one? It's a 128. How about this one? That's a 64 plus 1. That's a 65. How about this one? That is a 128 plus 1. 129 plus 4 would be 130. 129 plus 4, 133. I got that one right, and we're done. Okay. All right, so you've got all these different conversions that you can use. And again, a link to this program is available in the description of the YouTube video if you'd like to play with that. When you're done with this, 16 will get you out. Maybe not. 16, Q will get you out. There you go. Q will get you out of the menu. All right, that's all I have for you. I hope that you find this useful in converting between these different bases. You can always follow me on Twitter at Mark Baggett or email me mbaggett@sans.org. Please do check out SEC 573. You see a link here to it and a link in the description of this video, as well as SEC 673, my advanced course, and the SEC 406, which is the Linux security for information security professionals. Thanks.